the warm-up question for today, we're going to be talking about hourglasses a lot. So the warm-up question is, if you had an hourglass on a scale, like you're reading the mass of an hourglass with sand in it, is the weight of an hourglass when the sand is falling heavier, the same, or lighter than when the sand is not falling? That's the question.
Right. Okay. So
how does the reading on the scale change when the sand is falling compared to not falling? Because
our intuition, and I think our intuition's right here, when it's all in the bottom, it weighs some mass. And I think that mass is the same if it's all in the top. You just flipped it real quick, set it back on the scale.
Right.
It's going to read the same thing. Or maybe you plugged it somehow. It doesn't matter which direction it is. It's going to weigh the same. Now, I think the thing that's going to throw us through a loop a little bit is when it's falling, the sand isn't in contact with anything.
Right.
With the hourglass, which is in contact with the scale. So why would its weight be adding stuff? Or just to throw another thought in there is it's falling and then impacting the bottom of the sand beneath it. Does that impact add force to it? Makes it heavier. Like if you drop a bowling ball on your foot.
Exactly. Yeah. So I think the way to think of it is imagine standing on a scale yourself, holding a bowling ball, and that there's some number on the scale. You're just holding it. Drop the bowling ball. For a moment, the scale's lighter because the bowling ball isn't being weighed, right? So it's just your weight, not your weight plus bowling ball weight. But then the bowling ball slams into the scale or your foot. The scale all of a sudden gets heavier. So that's the sand falling through the hourglass, hitting the bottom, and the scale is reading a higher number than when the sand was only at the bottom or only at the top.
Right, because it's imparting some impulse to the system.
So it's heavier as the sand is falling and hitting the bottom. It's lighter as the sand is falling, but is in the air, hasn't touched the bottom yet. And then it's in between when all the sand is at the bottom or all the sand is at the top. And those two are equal.
Okay. So to reiterate what you just said, if I want to make sure I understood you correctly. Okay, I have all the sand at the bottom. I'm going to walk through an hourglass, maybe. I have all the sand at the bottom, and
it reads 100.
Yeah, it says 100.
The scale says 100. Yeah.
Okay, and then I flip it over, and right at that very second I flip it over, it still says 100.
Right.
But then a snap of a finger later, there's some amount of sand that has fallen from the top but has not hit the bottom.
Right.
And in that moment, it's lighter.
Right. Reads something. 95.
Yeah.
99.
It says 99. And then when it hits, now it's impacting the bottom, which is then moving the scale.
Right.
And so now it weighs 101.
Right.
And then, another one falls, and that process just repeats going through itself. And then, if you get a constant stream, I guess it's always weighing 101 or something.
Right. But it's always higher than the actual weight of the sand in hourglass.
I want to try that.
Yeah, that was a physics Jerry question. I don't remember exactly how it was laid out, but you had to rank them, or I don't know, something like that. I think it was like you had weight as a function of time graphs, and you had to select the correct graph based on like flipping an hourglass over on a scale, something like that. Right. Yeah.
So could we contrast that really quick with, this isn't about hourglasses, but it's about falling things that are weighing. Is you hear that problem a lot in physics. A guy driving a truck of birds, across a guy driving a truck of birds, his truck and birds weigh 5 tons. The truck weighs 4 tons. He has a ton of birds on his truck.
Okay.
The bridge up ahead can only hold 4 tons. So right before he crosses the bridge, he, reaches back and rattles all the cages and spooks the birds so they start flying as he's going across the bridge. Does he make it across the bridge?
I don't think so. If the birds, we treat them as like helicopters or like hovercrafts, because they have to push air downwards, like it's a sealed vessel of air. The way the birds get lifted is the air. Like if he did that and all the birds were at the top of the truck, and then the moment he drove across, all the birds stopped flapping and then started falling back to their perch, then yes. But I think if they're flapping their wings, the upward force holding the birds up is a downward force in the air, which presses down on the truck with the same. Actually might make it worse because it's trying to accelerate the birds upward.
Right. Yeah.
That's my answer.
So I think that's an interesting contrast. I feel like I hear that question a lot. Like I definitely heard it a few times in my undergrad career. And so like when you first asked me this hourglass question, my thought was immediately like, oh, it's going to weigh the same or something. Like I got to figure this out.
Yeah.
Because of the bird issue that you were just talking about. But yeah, I think a common thing that people say is exactly what you did. If the birds stop flying during the course of the bridge and they just fall, then yeah, we're okay. And that's kind of what's happening during the sand is it's just in that fall mode until it impacts. It'd be like all the birds are flying and then suddenly they get gassed and die and all fall and hit the ground at the same time.
Yeah. As long as you're past the end of the bridge, you're fine.
Yeah. Okay, so should we move on to our actual question for the day?
Sure. Yeah, let's get started.
I'll be honest, I probably looked at this video a couple days after you showed it to me, and then I thought about it a little bit, but I didn't do anything, and I didn't really start writing anything down until about an hour ago. Oh,
yeah. Well, you did more than I did. I didn't write anything down. Why don't I start by just describing what's happening?
Sure.
So what we're trying to explain or figure out how it works is a little device. It's like a desktop tube of water, and then inside it, so it looks like an hourglass, like it is an hourglass, but it's inside a tube of water. So imagine just an hourglass in a tube of water, and the video starts with the hourglass at the top of the tube, so it's like floated. It somehow has floated its way to the top, and then the person flips it over. Sand starts to go from what's now the top of the hourglass into the bottom, like a normal hourglass would. But while it does that, it starts floating up towards the top. So initially it stays at the bottom. So apparently the steady state, I feel like I said that a lot the last time I recorded also, but the steady state is the hourglass with sand at the bottom, but the hourglass itself has floated to the top. So if it's in that situation, if it's in that state, it's going to stay there happily forever. So sand at the bottom of the hourglass itself at the top of the water. So you flip it over, the hourglass sand starts falling, and then it still stays at the bottom for a while, but eventually it looks like it kind of lifts off the bottom and then floats to the top. And so how does the hourglass, how does that start to float when the sand moves from one part of it to the lower part? I don't really know. So I've thought about it and I've stared at it a while. I got nothing. I think we can go through some basics of just things we can rule out and maybe some ideas of what would have to be changing in order for this to happen. Yeah,
I think like we could talk about like also maybe like why isn't it immediately obvious like what's going on? What's the when we see it through like a physics lens, why can't we just like go, oh, that's it, or that sort of thing?
Yeah. Oh, obviously that's how it works.
Yeah. Yeah. So actually I was wondering, can we go over the device again real quick? Because I think
I missed something.
No, I don't know that you missed anything. I think it was just quick, and maybe
okay.
If this turns out to be just a complete reiteration of what we just said, we can just cut it. But
sure. Do you want to do it?
Well, no, I think we should. I was thinking like maybe start by thinking of a like a ping pong ball in a sealed tube of water.
Okay.
Right, and then you flip it, and the ping pong ball rises. So you kind of get an idea of what's happening, and then we replace that with an hourglass.
Yeah.
And so when you flip it, like if it would behave just like a single unit, like a ping pong ball would, it would just rise just like the ping pong ball.
Right.
Because it was floating before. Yeah. So when you flip it up, it's going to float again.
Right.
Okay. Well, yeah. So I don't know. Maybe that's not even a reiteration of what the device is. It's just kind of like my initial thought process of, okay, and then that's what I'd expect. That's my intuition. It was saying.
I just had a guess as to how this works. And if I'm right, that makes me mad that that's what it is because it's really stupid.
Okay. Well, yeah. So let me finish.
I think I'm right.
And then we'll go to your guess.
Okay. It just hit me how this thing works. So yeah, the thing doesn't rise instantly. There's definitely a delay until the sand falls to the bottom.
Which is the weird part.
That's the weird part.
That's
like
strange.
It doesn't just float to the top like it was initially.
Yeah, so it doesn't behave like a ping pong ball. It'd be like if you flipped it, you had ping pong ball in there, you flipped it, and the ping pong ball just sat there for, a certain period of time, and then it went up.
Right.
So that's what this hourglass is doing.
Yeah.
And it seems like it's triggered by maybe a certain amount of sand transferring from the top half of the hourglass to the bottom half of the hourglass.
Right. Maybe I'm wrong. I'm looking at it over and over again, and I don't think I'm right.
Okay. Well, what are you thinking?
I was thinking it's friction with the hourglass rubbing against the side of the glass cylinder holding the water.
Oh, interesting.
And it's like because the sand's when you flip it over, sand is now at the top of the hourglass portion, and the bottom is air. Oh no, that doesn't. Like imagine it wasn't an hourglass, and you had two bulbs, one filled with sand and one filled with nothing, with air, right?
Uh-huh.
How would that thing float? It would float by flipping over and having the sand on the bottom and the air on the top, right?
Yeah. Like if they were two separate containers, you can't transfer between them.
Right.
Yeah. The stable state is for the glass bulb to be up.
The one with the air in it would I would think pretty much instantly flip. If you think of the hourglass not being an hourglass, meaning don't allow sand to transfer from one side to the other. What if it was sealed and sand couldn't move from the top to the bottom like a normal hourglass does, but instead it's just sand on one side and air on the other? If you put that in water, how would it float?
Right. Yeah. It's going to want to, assuming, it's not in a perfect line, it's at a slight angle, right? A small perturbation, then it's going to want to flip it. And then
if you just drop that in water, the air side would want to go to the top and the sand side would want to dangle down below, hang below.
Right. There's some torque going on.
Yeah. So this cylinder that's holding the water is just barely, a couple millimeters wider than the hourglass. So I think when you flip the cylinder and the hourglass is on the bottom, the sand is at the top and the air is at the bottom of the hourglass, and that hourglass wants to rotate, but the glass of the cylinder gets in the way, and I feel like it's kind of like wedging itself inside the hourglass, like it wants to rotate, but that rotation is like pushing against the side of the cylinder, and that causes this hourglass to stick kind of like to the side. And then once the sand does get to the bottom, then it's happy to float as you would expect, right? Because there's no more reason for it to try and twist, and it's not rubbing up against the sides anymore, and it does end up floating to the top.
I could definitely see how that could be it. I don't know. We'd have to think about a little bit more of the math on how to show that, maybe.
Yeah. A couple points. One, the hourglass rises really slowly. Like, don't think of a ping pong ball. It's something that's just barely less dense than water, the hourglass part of it. It rises, like, I don't know how long this cylinder is, maybe a foot, let's say. And it looks like it would take 5 to 10 seconds for the cylinder to cross from the bottom to the top. Or sorry, for the hourglass to cross from the bottom to the top as it's floating up. It's really slow. So my point is, when the hand comes in and initially twists or rotates the cylinder, flips it over, the hourglass doesn't move at all. And I would think there'd be a little moment of kind of like, well, I'm not sticking to the side yet. I'm going to jump a little bit before I start to want to twist. There would be some kind of wiggle that would free it for a second, but that doesn't happen. And I'm saying if it was like a ping pong ball and it was weighted or something like that, imagine a ping pong ball with something heavy that could stick to a ping pong ball, like a nail. Imagine a nail driven into a ping pong ball, like a big nail. If the nail is at the top of the ping pong ball, you could imagine this happening. Like the thing would want to flip over, right? And kind of might get stuck, even though it would naturally float. The whole ping pong ball nail system would float.
Right, yeah. So it's not enough. If you just throw it in water, it's going to float. Right.
But yeah, I feel like the nail would tip into the side of the glass, and the ping pong ball that's maybe a bad example, but I would imagine there would be some kind of wiggling, like it would kind of shimmy itself into position of getting locked if the hourglass was actually sticking against the side. And I don't see that happening. But it is moving really slowly, so
right.
Maybe it's just not that urgent for it to get up to the top, to float towards the top. I'd imagine it's much more urgent for it to tip over and get into that happy, stand on the bottom state.
Yeah, we could imagine. I'm watching it right now. Okay, we could imagine let's say we did that experiment. I've been
watching it this whole time, just looping over and over.
We put a nail on a ping pong ball or something, or we glue a little copper weight on it. So we glue those two things together, and you put that in this system. Right. What we expect then is the ping pong ball to float to the top with the weight at the bottom. Right. So you say you're in that position right now.
Right.
And then you flip the whole thing over.
Mm-hmm.
Now the mass on the top is going to want to go down to the bottom.
Right.
But we know the system, the two things combined, float.
Right.
So if there's enough buoyant force up, then the rotation, if it gets trapped between the two walls of the tube,
mm-hmm.
if the torque that's turning it, trying to put that weight on the bottom, isn't heavy enough, or isn't strong enough to put a lot of friction on the side of the wall, the buoyant force is still going to push this thing up.
Yeah. Yeah. And I think I figured, I thought of a good analogy of how this could work in you could actually see it working. Almost like a ratchet, but imagine what do they call it? Like corrugated pipes, they're kind of rippled.
Yeah.
Like those drainage pipes, something like that. So it's like ribbed, like the pipe is ribbed. Imagine the weight, or let's go back to the nail, because I can imagine that thing, you flip over the corrugated pipe of water, the ping pong ball is at the bottom with the nail sticking out at the top. The nail wants to rotate to the bottom, but it hits the side of the corrugated pipe and gets locked into one of those ribs, right? The little ridge. And so then the thing's stuck. The ping pong ball wants to go up. The nail wants to go down. The whole system of ping pong ball nail also wants to go up, but it's being held by the edge, by the side of the pipe. Does that make sense?
Yeah, yeah.
So I imagine that's what's happening here with the glass of the hourglass rubbing against the glass of the big cylinder.
Right.
And it's just getting caught and trapped.
I can definitely see that, and here's kind of one of the thoughts I had was if you go to you don't exaggerate the tube, you don't go to a corrugated pipe, you just mm-hmm. use friction.
Mm-hmm.
If the amount that it wants to rotate isn't a lot, I'm trying, if there's not a lot of torque on it, then the friction mm-hmm. between the wall and the ping pong ball nail system is going to be small. So if the buoyant force is still real large, it's just going to push the whole thing up.
Right.
And it'll float. It'll just float with the nail on top mm-hmm. until it hits mm-hmm. the top. But if the buoyant force is small enough, then it's going to get caught.
Right.
So that's what's going to keep it there. So the fact that this thing is floating really slowly means the buoyant force is almost equal to the force of gravity on this.
Right.
So
it's pretty close to neutrally buoyant, but it is just barely not neutrally buoyant.
Right. So I think that's a really good, put that in the pro side of your friction idea being right.
Right. Yeah. Because there's definitely, imagine a piece of glass a wet piece of glass and then another piece of glass next to it, there's not much friction between those two things, right?
Right.
And imagine how hard, this hourglass is about the size of a thumb. It's a small hourglass. There's not a lot of sand in there. There's not a lot of weight trying to tip this thing over. So there's not a lot of torque, getting this thing to rub up against the side of the glass. But I guess it's enough.
But here's the thing, though. If you watch it, when it's at the bottom, wait till it starts to go up. And it stays in one position until it gets about a quarter of the way or so. And then it'll start to go back and forth, the whole system in the tube.
Back and forth, like left to right?
Left to right, yeah.
Oh, yeah, it does. It kind of bounces off the walls a little bit.
Right, which would mean that it's now in a more, there's not torque on the system. It's not trying to rotate, so it's not wedged anymore. It has the freedom to move back and forth. I think you might be onto it.
Yeah. That's a bummer. That's definitely not as exciting as I thought it was.
Well, I took a different route, a totally different route.
Okay.
It's more mathy.
I still could be wrong. I still could totally be wrong. So,
but I like it. I think we have two little bits of info looking at it that are for that. I mean, we expect there to be that torque present.
Right.
It doesn't initially move back and forth, meaning it seems like it's wedged in between the two walls of the glass tube. And then, lastly, the buoyant force is really small. So all those seem to lead towards the friction idea being a possible answer to this.
And let's also describe when it starts to float up. It's not instant, and it's not when like half the sand has gone through, and it's not when all the sand has gone through. Maybe a quarter of the sand has gone from the top to the bottom. Yeah,
it's a little difficult to tell because it's not linearly the same, because the amount that's left in the bottom, part of the inverted pyramid, even though it could look like a lot, the base part of the pyramid has a lot more volume to it, so it's hard to exactly guess it, but it looks like maybe I would say a quarter to half, somewhere in there.
That's what I would say too. So I think that leads to the evidence that that tipping rotational torque pressing against the side of the glass force is decreasing as the sand moves to the bottom.
Right. Yeah. Like if we go back to our ping pong ball nail system, it's kind of like, okay, imagine it's stuck there wanting to rotate in your corrugated pipe, and somehow you could magically pull the nail through the ping pong ball
to the bottom. Right.
Now it's going to float.
That's what's happening. Yeah. Exactly.
I really like it.
I mean, I feel like it's right, but I don't like it because it's stupid. It's not like a cool, the density is changing and it's floating, work out Archimedes principle on this thing and see how it changes with sand in the hourglass. But
well, I mean, we can talk about, I think it might be worthwhile talking about the mass isn't changing of the system. Mass is the same. So the net force is on the two objects, at least in terms of just your basic buoyant and mass force. If you put this thing in water, it should be the same in terms of net forces.
Right. So what I was hoping for was a solution that didn't depend on the cylinder of water. I was hoping for something that says, let's take this hourglass and put it in a pool, a huge pool, and turn it over when it's on the bottom and watch it float to the top eventually. But based on my solution, that's not going to happen. The cylinder itself plays a crucial role in how this thing works.
So maybe there's some better way to talk about this without referencing all the math. So, because people can't see the math. But essentially what I did here, I've decided to treat this thing as two cans. This is why I just kind of depicted them as on top of each other. And then I said, okay, let me consider all the forces acting on the bottom cam. Or I guess, this is my a mistake. I don't know. But so what I said is, okay, on the bottom can, we have the pressure times the area at the top of it going downwards. And then, so that's the negative P2A. And the pressure on the bottom of the can times the area going upwards, it's P3A, minus its mass, or its weight, MBG. Right. And I said, okay, now if the top object has some net force down, we'll have to subtract that out too. So if that net force is, that would be the mass of it going down plus, its buoyant force essentially. And then the next line, you see, okay, that the two forces, Newton's third law, cancel at the interface between the two. And so then you just end up with this equation that says, okay, the sum of the forces on the bottom is equal to this system. And, essentially this is really boring, but I think you could just, if all my math is right so far, my physics, then you could just essentially set the volume of this thing and the masses to be such that you'd be able to neutralize this force once the bottom weighed more than top or top weighed more than bottom. Does that make any sense?
No, I don't. I think you just did a complicated, like Archimedes principle calculation for the entire object, but you did it for two separate objects.
Right. Yeah. So it can boil down to the entire object.
Like rho is the density. So to explain what's happening, you have MT and MB, mass top, mass bottom. They have it's assumed to be a cylindrical object with area A, cross-sectional area circular A, and it's upright, so it's like having a can on your desk. And then half the height is R. So the top has a height R and the bottom has a height R. And then you worked out the pressures at the top, the middle, and the bottom of the object, and then the weights of the two different objects, and then balanced all the forces on the bottom object. But then it ended up that the sum of the forces on the bottom object is equal to...
Yeah, I mean,
so rho is the density of the fluid around it.
Right.
Right?
Yeah.
So you have 2R times A. That's the volume of the entire object. Right?
Yeah, because the height of the object is, each can, as I said, is height R. The height of the object is 2R. So then 2AR is the volume.
And then rho G, density of the fluid around it, the water, times G, times 2AR. That's rho G V. So that's the buoyant force, right? Which is the buoyant force is equal to the weight of the fluid displaced. That's your Archimedes principle.
Yeah, right.
So you have weight of the fluid displaced is an upward force, and then on the subtracting from that is MB plus MT. So the sum of the masses, the quantity of that times G. So the buoyant force up minus the weight of both objects down. Now, I don't know that that's right. If sum of the forces equals that, I don't know that that's the sum of the forces on the bottom can.
I see what you're saying. Because it's like for the whole object.
That's the sum of the forces on the whole object. And I think the problem is you kind of calculated the force of the top on the bottom and kind of lumped it all together. Trying to think of what the mistake in the logic is. I think the mistake in the logic is you called what you kind of curly bracketed and said top can. Uh-huh. That should just be some F.
Okay.
And then there should be an equal F upward from the bottom onto the top. But since this isn't balanced, I don't know that you can just say those things are necessary. I mean, I know they're equal from the third law. Like that's definitely true. But I don't know if the F of top on bottom is equal to the other forces on the top can. Because it's not in equilibrium. It's accelerating, right? So sum of the forces doesn't equal zero. So the interaction force doesn't equal all the other forces.
All right. So, okay. If we're going to that top equation real quick. Okay. So everything except the curly brackets, you think we're good on.
Yes. That would be the sum of the forces on the bottom half of that can if it was just by itself in a fluid.
Right. Okay. Then we have to add, if the force of the can above it is downwards, the net force is down.
Right. So let's just assume that. It could be upward, but let's just make a guess that it's down.
Right. Then we have to subtract that force as well.
Yes, there's a downward some interaction force. Yep.
Okay. And then what is that force then? It's the mass.
What is it equal to?
Yeah.
Well, then we have to go into, so you wrote out some of the forces on the bottom can. You need to write out some of the forces on the top can. But my problem is you're making the assumption that some of the forces equals 0. That's not true.
I don't think I've assumed that anywhere actually yet.
But you did by not including any sort of acceleration in that top can curly bracket part. So write out some of the forces on the top can. Okay.
All right. I see what you're saying. Can we make the argument without me having to rewrite this real quick? Mm-hmm. Okay. What about when look at the state where it is in equilibrium.
Okay. If it's in equilibrium, then what you wrote is correct.
Okay. Minus, I guess there's technically a normal force on the bottom can.
Due to the top can?
No. Due to the floor or whatever.
It's sitting on the bottom.
Yeah.
Oh, that's an interesting question. Going back to the original video, because let's imagine this thing was in this tube, this cylinder of water was infinitely long.
Uh-huh.
At some point, all the sand would be on the bottom of the hourglass, and the hourglass would be floating upwards slowly, like we see it, right?
Right.
It'd be gradually picking up speed because those forces are not balanced. It is not equal to, the buoyant force is not equal to the weight. So there would be some acceleration. Well, I guess it could reach like a terminal velocity in the fluid, but let's ignore that for now, right? So it's accelerating upwards in this infinite tube of cylinder of water.
Okay.
You follow me? It's moving, and then we flip it. The infinite tube, we flip.
Right.
What happens?
Yeah, so...
Because now we don't have a normal force. Like, I did that to get rid of the normal force. Like, we don't have to worry about it sitting on the top or bottom. And I think we'd have the same situation. I think it would just stop in place if my friction idea was correct.
Yeah, or I mean, with momentum, it slowly come down, to a stop somehow.
Yeah, it would kind of like drag on the sides.
Yeah.
And eventually stop.
And then until the thing flipped, it would go up.
And then it would keep going up.
Okay, let me add this really quick to the argument. See if this does anything. I picked a bad variable, I think, but I think it's still kind of valid, maybe. Okay, so I'm trying to think about this thing when it's just resting on the bottom.
Okay.
And okay, maybe I need to include a normal force, and maybe that would help. But okay, so the last bits that I've added is, you can see, I didn't label my lines, but there's a equals rho GV minus mass of the bottom times gravity minus mass of the top times gravity.
What's A?
Okay, then I'm saying
little a.
Little a. It's some constant. It can be, I'm saying, what if the mass of the top is heavier than the bottom?
Okay.
Then you work this down. Okay, and then I said, okay, we're in the equilibrium position. That's where I set it equal to 0. Because the net force is, I guess I should add a plus n there.
Okay.
But, okay, then the A has to be, the mass of water displaced minus 2 times the mass of the bottom in order to keep it down.
Okay.
So once A gets smaller than that, would that be right? Then it would be floating. I don't know. That's why I'm trying to work out. I haven't thought like the logic through yet. I've just put a bunch of numbers on a piece of paper.
Mm-hmm.
So I'm trying to say is if you imagined it as two cans, and then the top can was holding down the bottom can.
I think we're stuck in a loop of, like, I don't know if circular logic is the fallacy, but we did something, we assume we're working incorrectly on this problem. So hear me out as to why. So at some point you wrote sum of the forces equals 0. That's on this paper right now.
Yeah.
Right. So that means that the bottom can is not accelerating up or down.
Right.
But that means that the top can is also not accelerating up or down.
Right. They're both just resting on like the bottom surface.
Ah, right. Okay. No. Okay. I think everything's okay then. Yeah.
I think if I'm, or you can imagine maybe it's neutrally buoyant, one of the two.
So my problem was thinking that it was neutrally buoyant, because if it's neutrally buoyant, there's no reason for the top can to touch the bottom can and to apply a force. Like, you can just set them next to each other and they won't press on each other if they're both neutrally buoyant.
Right. So I'm assuming that for some reason the top can, let's say, is not neutrally buoyant. It's heavier. It's going to sink. The bottom can is lighter. Maybe it's going to float. The two combined is neutrally buoyant. Maybe.
Okay.
So that's why I'm subtracting off that top can part. Is I'm saying, okay, if the top can is not neutrally buoyant, it's heavier for some reason. It's going to put a force down. Mm-hmm. Then you work through all this, and then I'm saying, okay, how much heavier? What is this mass of the top can? Let's just imagine it's the mass of the bottom can, and then some amount more, A.
Right.
And now I want to say, okay, well then, like, what does A have to be to keep it 0, to keep it neutrally buoyant?
Yeah, how much heavier does it have to be?
Yeah, and that's what I solved for, I think, right? Mm-hmm. And then so it's saying, A has to be the mass of the water displaced, that's rho v, minus 2 times the mass of the bottom. So does this mean you could also potentially just set this up in a pool and it would work?
No, because I think everything we're assuming is these are point particles and not. Oh, I mean, it's kind of like an unstable equilibrium in this configuration with the heavy, more dense thing on top and the less dense thing on the bottom. Like, they'll want to slide past each other and have MB, the bottom one, float all the way to the surface.
Right. They're going to want to do the flip that you're talking about. Yeah.
Right.
I'm saying, imagine,
so just ideally perfect situation where they couldn't do that, then they would just be stuck. Maybe it's not even friction then. Maybe it's just that they can't rotate. No, that doesn't make sense.
No. They definitely can rotate, and that could cause friction.
Well, I was going back to the hourglass and saying maybe they don't need to, maybe it doesn't have to be stuck to the glass, but it does. Because flip it now and have the heavy one on the bottom and the light one on the top. If they were actually just two separate things, they would just pull apart from each other and separate. But
right.
Now we'd have to, that force between them would be kind of like an attractive force. So you basically found the point where, in kind of ideal circumstances, the amount of sand that would have to move from the top to the bottom for this thing to start moving? No, that's not what you found.
I think, if A is less than the amount of water, the mass of the water displaced, minus 2 times the mass of the bottom one, it'll begin to float.
Mm-hmm. So the equation is the extra mass is rho times V minus 2mb.
Right.
So density of water times the volume of the full can, the combined both of them can. Subtract from that twice the mass of the lower half, which is, we're assuming, less massive than the top half.
Right.
Can we play with this and say, can we make that difference in mass, that value you called A, negative? What does that mean? Like if 2mb is greater than rho v?
Okay, that would mean if you go to the equation above, that the minus ag term is positive.
Right.
And so I think you're going to get a positive force.
I think all it's saying is that the top half is now lighter than the bottom half.
Yeah.
And the things would just separate and float away. Or there's some sort of attractive force between them.
Yeah, I guess so. What I'm maybe suggesting, I do like your rotation idea, and I think that could be the answer. I'm not saying this is more right than yours, but what I can see here, if I did everything correctly, then it's that it could be built such that it'll work without having to rotate. It'd work in a pool. But okay, all right. So rho v is the mass of the water, right? That's displaced.
Right.
So is there? Yeah, I'm trying to think. It seems like we should be able to kind of play with this a little bit and see if we can see if it makes physical sense. I'm struggling to figure out how to do that, and I think that's what you're kind of getting at too. Is like if we, is this situation where you have the mass of water displaced minus 2 times the mass of the bottom you can create that presumably, right?
Mm-hmm. Can we write volume V in terms of the mass of the two halves? The volume should be the mass of the two divided by the density of whatever the can is made out of. Oh, but we're assuming they're two different objects, so I guess we can't really do that.
Well, we could just separate it into two, the volume, and do it for each individual.
It's going to get really messy.
Thing. Look.
I'm just wondering if maybe that minus 2mb, I don't know why that throws me off. But it does make sense because make A 0, which means they're both equal mass. Make the difference in mass 0, the little a.
Uh-huh.
That would just say that rho v, which is the mass of the fluid displaced, is equal to 2mb, which means the mass of the fluid displaced is equal to the mass of the full cylinder, because 2mb at that point, if A is 0, if the difference in mass is 0, then 2 times the bottom mass is equal to the full mass, right?
Okay, yeah, right.
Which is equal to the mass of the fluid displaced, which means that the buoyant force equals the force of gravity on the entire can combined, which means it's neutrally buoyant. We're kind of making two assumptions. One is that it's not accelerating, and the other is that there's no difference between the top and bottom masses.
Right, yeah. I'm trying to... Yeah, I'm assuming it's not accelerating because at the beginning of this whole process is it's not accelerating. Yeah, I think it's because, I could replace, let's see, I want to know when this is less than or equal to 0. When A is greater than or equal to rho v minus 2mb, the force is downward.
Yes.
Which then there's presuming if it's resting on the bottom, there's a normal force to keep it up.
Right.
And so then those two are just going to counteract until A is equal to rho v minus 2mb. And then at that point, it's going to flip. A will flip, and then so the forces will be greater than 0, the sum of the forces, so it'll move up. This got real math heavy, and that's not what I wanted. We cut out a lot of this.
Yeah, it's not too complicated, but it doesn't make sense. I don't know why moving mass from one side of the object to the other would change the net force on the whole object. No. That's why I just said what the problem is. The sum of the forces equation that we're working with A equal to 0 is only for the bottom. Right?
Okay.
So that means all of a sudden acceleration being, or some of the forces being downward, right? When A is big, that means there's more force on the bottom half pushing downward. Good.
Sorry, okay.
A being big, the difference in mass being
Yes.
large means there's more force pushing downward on that bottom half of the can.
Yeah.
A being small, A being less than what we required for it to be 0, balanced, that means that there's an upward force on the bottom half of the can. Is that right?
Upward force on the bottom.
On MB.
Yeah. Yes, that's right.
But we haven't said anything about the whole entire object. I think A being small, the difference in mass being small means that the top is not pushing that hard on it, right? Oh, this is more complicated than we're thinking. MB is changing in our video, the little GIF of the hourglass.
Definitely, yeah. So is that, yeah,
okay,
MT and MB are changing at the same.
That complicated things to a point where I'm happy with, because I was assuming MB was constant. I was not understanding what was happening. But now that I realize, yeah, okay, obviously the bottom half is gaining mass as the sand falls. So all we're saying is that the bottom half gets bigger and the upper half gets smaller, and the upper half being smaller causes the thing to float upward. No, well, it does, but all that's not what this equation is saying. All this equation is saying is that there's a net upward force on the bottom part.
Right.
But we haven't said anything about the top part.
Right, but my logic was if the bottom starts moving up, then the whole, because they're really attached, the whole thing's got to be moving.
I think that's true, because the top part is definitely not massive enough to weigh down itself. Is that true?
Well, let's see. If A is equal, if A is equal to rho V minus 2mb.
A is the difference in mass between the top and the bottom.
I guess it is. Then that's a really good way to think about it. That was a good insight that I didn't see. That what you just said. That A is the difference between the mass and the top and bottom.
I thought that's what we've been defining it as.
Well, I mean, it is defined as that. When I wrote it, I wrote mass of the top is equal to MB plus some extra weight. It just didn't click in my head that extra weight is the difference in mass between the two. I'm very slow. Then MT is equal to minus MB. Does that help? Okay, so I mean, like if you say A is equal to, the difference in mass is equal to rho V minus 2mb, then MT is just rho V minus 1mb. But I don't know what that means. That gets us.
So rho V minus anything is just the mass of the fluid displaced minus anything else. So all that's saying is that it's the mass of the fluid displaced minus the mass of the bottom half. That's equal to the mass of the top half, which is true when it's neutrally buoyant.
Okay. Yeah. Okay. If you said the MB part of that, the difference in mass is equal to that, is really equal to the mass of the system. I'm just calling it big M minus MT. Does that? No, okay, that doesn't enlighten anything for me. I have to like think about this more, but
I think I get what you're saying, and I think if we did this in a pool, it would flip. Like it would just want to flip too much to do this, but I think what you did is right. Like I think it does show that it could be possible in a pool if it's like perfectly, like I don't know. I was going to say something stupid. Like if we somehow made an hourglass with a hole in the middle, like just drill through the middle from the top to the bottom of an hourglass and thread a rod through it. And then we flip the rod over, but it's the same thing as the cylinder of water.
Right. I was thinking the same thing. Yeah. And then I ran to that same conclusion. Okay. Well, maybe. Okay. If this is, sorry.
But maybe, so I think what you just proved though is that you don't need friction for this to work, because nowhere in here is there a friction force holding this thing down.
Yeah. I agree. Like I included a frictionless thing. We could add more forces through friction.
That would only help everything. But I think you just proved by writing it out without friction that it would work.
Yeah, as long as you set the masses correctly, maybe.
I think I have one sentence that could summarize both of our work. Basically, a unified theory of how this works.
Okay.
If we constrain an hourglass to one-dimensional motion, this will happen. I think that's all we did.
Right, yeah.
I was thinking like it wanted to rotate, but it couldn't, and it was stuck on the sides. I don't know that you need it to be stuck on the sides, and I think you just proved it. But what you were working with is assuming it's just up and down, and that's it. All you did was work out vertical forces, not tipping, nothing like that. So if you just constrain an hourglass, it'll do this.
Right. Yeah, I think that's a good way to put it. I added this one to Slack. Sorry to think of the name.
That's the neutral buoyancy condition.
Right. But I thought that was kind of weird. This kind of confused me. I'm saying, okay, MT by definition, M is the mass of the system. Big M. So the mass of the top is by definition the mass of the system minus the mass of the bottom, assuming the container doesn't weigh, or even if it does, I guess. So then you solve all that and you get the mass of the whole system has to be equal to the amount of water displaced.
Right.
So does that say then that?
Yeah, I think that's just the condition for the thing being able to float at all, no matter where the mass is, whether it's the top or the bottom. Like, could we envision an hourglass that doesn't float at all? I think so.
Right. Yeah, we would just make it real heavy. Like imagine if we filled the bottom with concrete, and it was a very slow pitch drop experiment or something. Okay, so I think I'm working real slowly on this in my head. But okay, if you go back to that equation that says, A equals rho v minus 2mb, right?
Right.
Okay, well, just from that other little bit I just sent, rho v is equal to the mass of the system.
Right.
So the mass of the system minus 2 times the mass of the bottom is the condition that gets it to float. Does that help make sense? I got to think about it.
I think all that's saying is it's like a circular loop. Like all that shows is that the mass of the system is the mass of the bottom plus the mass of the top.
Okay. All right. I see that there. Yeah. Okay. I think you're right. But, we don't have to continue discussing the math anymore. I think we have swamped that out enough. Okay, do we have any other theories that aren't math related, hopefully?
No other theories. I think just saying constrain it to one dimension, like don't allow it to flip or rotate, and it'll do this. And yeah, could we build one of these? Like, could we design an hourglass that does this?
Definitely try. I guess here's the thing I'd like to know, that I'd like to see is if through this little set of equations, if we can predict the ratio of sand, that's what I want to know, I guess, is what is the ratio of sand that makes it float? Because we can see that.
Right.
Roughly.
How much of the total sand percentage-wise needs to be on top versus the bottom? If we ignore the mass of the glass that's holding the sand in the hourglass, like just because that the sand is the thing that's moving. So we found the difference in mass required to get the thing to move upward.
Right.
I can't see it.
Yeah, I'm dividing stuff by other stuff. Mm-hmm. And it's not necessarily helping me. I hate when I get stuck in a circular mathematical loop. Mm-hmm. I just wrote like 3 equations and they ended up back with like the same stupid thing.
Yeah.
Yeah, okay, maybe we'd have to think about it more. But so we can look it up later, over this next week and try and decide what we think. But and I can LaTeX, maybe, if I can draw pictures. I can LaTeX this argument up and we could post it to somewhere.
Okay. I think we cracked it. We're going to think about it a little bit more and come back with a more rigorously analyzed explanation.
Yeah, or maybe see what other people say and see if they agree.
Maybe there's stuff online about this. Do we want to go there? I think so. I think if we just look it up, I think that's valid.
Yeah, and see if people tend to agree with us or not, and then.
Right. This is like, the podcast is like, you take the test in class and then you're given a redo chance and you just go home and it's open anything. Just open note, open internet, ask your, friend who has a PhD in physics. Although that didn't help me here. So
if you want just a very brief glimpse, I don't know if you want to include this or not, but the top comment of on Reddit, where I don't know if that's where you grabbed this from, but
I think I did. I think I saw it and I purposely didn't click on I just looked at the picture and I just pulled the picture and I didn't read anything.
Yeah. So maybe we want to include, this is from user Lufa.
Okay.
Submitted this GIF, and user End112016 says, and he has the it looks like it's the top rated comment. He says, I had one of these once. When the air is mostly in the bottom bulb, it tries to rise and the top tries to sink. So the hourglass tips a little and gets jammed. As the sand falls down, it straightens out and can rise.
Well, that's score 1 for me.
Right? Yeah. So the very first thing, he agrees with you.
But I don't know. I mean, I don't think it needs to get jammed. Like, I think you just showed that it would just do this. I don't really know why, though. It still bothers me that it's not neutrally buoyant to begin with, and then it crosses neutral buoyancy. Like, it goes from negative buoyancy to positive buoyancy. That's still kind of not feeling good. The question is whether it would happen not in the cylinder. Like, let's remove friction with the walls and just work with an hourglass in a pool. And if you had the hourglass that could float in some configuration, which its ideal configuration is the heavy side down, so sand in the bottom half, nothing in the top half, the hourglass would float at the top of the pool. Like, everyone would say that, sure, I can see how an hourglass would float, and that's the way it would float. It makes sense. The question is, if you take the hourglass to the bottom, like grab it with your hand, drag it to the bottom of the pool, turn over the hourglass, and somehow force it to not flip itself back over, because now it has the empty side on the bottom and the sand on top, and it would want to just kind of flip, rotate. Don't let it do that, but somehow without friction. Don't let it do that. Some magical, I don't know, physics ice walls with no friction. Keep the thing in an upside down position with sand on top. Let the sand fall like an hourglass does. Would the hourglass stay at the bottom of the pool until a certain amount of sand has moved to the bottom half and then start to float up to the top like we saw originally? That's the question.
Right. Okay, I think that was a good explanation. And
Zach's math said yes. General intuition says no.
And which is why we're struggling so hard with it.
I think we both agree that my explanation of the friction and the tipping of the thing kind of like getting wedged, it does make sense. I don't know, there's not a lot of friction, but maybe that's fine. Like glass on glass with water in between, that's pretty not frictionful. So I don't know. I don't know if friction's enough, but maybe.
Yeah, I mean, you definitely know. I'm convinced that your description is happening either way.
Yes.
Because of the lateral motion that you see as the sand drains.
Right.
That's got to be happening. But whether it's the primary factor or just a contributing factor, I'm not sure yet.
Let's imagine like let's go extreme, a bowling ball and a piece of styrofoam. And attach them with like a rod, and then throw it in a pool and make the styrofoam big enough that the styrofoam would float and the bowling ball would hang below it in the pool, right?
Right.
That makes sense. Like that, there's a way to do that. Is there a way to flip that over, put the styrofoam on the bottom of the pool, the bowling ball on top, constrict them to not be able to flip over like they want? Would the thing just stay at the bottom of the pool? I don't think so.
Yeah, right. That's the thing that doesn't make any sense. It doesn't seem like it would. I don't.
Right.
My intuition says no. It would float back up.
Right. Even though it's like in an unhappy situation, like it wants to rotate and flip over, I think it would still float to the top. If the foam can support the bowling ball, it doesn't matter where the foam is. Like it's still going to pull
support
it up.
Right.
Yeah. But I don't know where your math went wrong. That's the question right now. Is like intuition, and yeah, we have another explanation, so everything seems like your proof should be wrong, but I don't know where. So that's what we need to dig into.